Math 2414, Surface Area of Revolution, Video 3, Surface Area Example 1. Before we jump into the example, I just want to point out the summary of what I said at the end of the previous video. That if you are rotating a curve around the x-axis and you want to find the surface area of the solid of revolution, then the surface area is the integral of 2 pi y ds, going around the x-axis. But if going around the y-axis, then your surface area is the integral of 2 pi x ds. Just remember that the variable that represents the radius is the opposite of the axis variable. Oh, and in both, ds can be either the square root of 1 plus f prime squared dx or the square root of 1 plus g prime of y squared dx, depending upon if your curve is given by a function of x or function of y. Alright, so let's take a look at this one. Find the lateral surface area of the solid obtained by revolving the graph of y equals the square root of 4 minus x squared over the closed interval, -1 is less than or equal to x is less than or equal to 1 around the x-axis. Now, it's not critical that you sketch this, but a picture can really bail you out sometimes. You may or may not recognize what this is the equation of. It's a semicircle. So in the midst of doing this, or prior to doing this, I think I need to give you a little bit of an FYI that if you don't know already, you need to file away among things that you know. First off, the reason this is a semicircle is that if I were to square both sides and get y squared equals 4 minus x squared, and then add the x squared to the other side, you should recognize that as the equation of a circle whose center is 0 and whose radius is 2. And if you don't recognize it as the equation of a circle, shame on you. You're in Calculus 2. You should know that already. So why is this a semicircle? Well, it's a semicircle because the original function was y equals the square root of, and square root as a function always comes out positive. This y is always positive, and so it's only the top half of the circle. But in general, what you need to know moving forward is that y equals the square root of a squared minus x squared is a semicircle with the center at the origin. And I should say the upper semicircle. Center at the origin with the radius of a. If you wanted the lower semicircle, you would just put a negative in front of the square root. So there's a little something to tuck away, especially those of you moving on to Calculus 3 or multivariable calculus, depending upon where you're taking Calculus 2. All right, but this isn't the entire semicircle. It's just the semicircle between -1 and 1. So if I were to substitute -1 and 1 into the equation, I would get the square root of 3 for both of them. So my curve looks a little something like this. This is the point 1 comma the square root of 3, and this is the point -1 comma the square root of 3. And notice that this is not a function of y because it would fail the horizontal line test. I have to view this as a function of x, so let's go ahead and call that f of x equals. All right, now we're going around the x-axis, and we're going from -1 to 1. So it would almost look like a barrel, if you will, if I took this curve and rotated it around. All right, so how are we going to find the surface area? Well, the first thing you have to decide is whether you want to do a dx or a dy integral, and that should be pretty easy if you have your function. Because this is the function of x, we're going to do a dx integral. Both of these have ds, which needs to be unpackaged, and because I need dx, this is the differential I'm going to unpackage. The square root of 1 plus the square of the derivative. Now, since we're going around the x-axis, the radius is represented by y, so 2 pi y. But do you see a problem with putting a y there? We're doing a dx integral. So instead of y, I'm going to replace it with what it's equal to so that I have the actual function itself. And in fact, let's just do that generically right now and replace the y with f of x. I'll tell you right now, the hardest part about the setup is going to be remembering whether you put a single letter here or a function here. Just remember, the letter is the opposite of the letter in the axis of rotation, but if you're doing a dx integral, then you have to replace it with the function that it's equal to. Or more generically, if this letter does not match this letter, if this variable does not match this variable, then you need to replace this variable with what it equals as a function of the desired variable. All right, so we're going to do this, but we're not out of the woods yet because we got to figure out the square of the derivative, add 1 to it, and cram it all under a square root, and put the original function out here, and integrate it. Oh, speaking of which, we're integrating from -1 to 1. All right, so let's get started building the square root part here. Because we're going to be taking the derivative and it's a square root, we might be better off rewriting the function as 4 minus x squared to the 1/2 power, so that we can take the derivative using the power rule followed by the chain rule. Technically, it's all the chain rule. All right, f prime, bring down the power, leave the inside alone, subtract 1 from the power, 1/2 minus 1 is -1/2, and then times the derivative of the inside, but the derivative of 4 minus x squared is just -2x. Let's write this a little more cleanly. Let's write it as a fraction without a negative exponent. I can't take advantage of the 2's canceling, since they're factors that match. Don't lose the negative though. Speaking of the negative and the x, both stay up top because neither has a negative exponent, but the 4 minus x squared to the -1/2 does. So let's put it back downstairs, and because of the 1/2, let's put it back under a square root. And I know what you might be thinking, you don't do calculus with square roots, you just said that. I know, but right now, I just did a calculus move, and I'm about to do 2 algebra moves. The algebra moves are square this and then add 1 to it. So let's square this. And that's really the reason I wanted the square root there, because it's really easy to square a square root, provided the radicand is positive. This one is. If I square both sides of this fraction, the negative becomes positive, the x becomes x squared, and when I square the square root, it cancels the square root, leaving me with 4 minus x squared. Okay, but now I have to add 1 to that. Let's move that over here. 1 plus the square of the derivative is going to be 1 plus that guy. Oh look, I'm adding fractions. I should probably get a common denominator, which isn't as bad as it seems. It's a 1. I can turn it into anything I want by putting something on top of itself. And since I want 4 minus x squared as the common denominator, we're going to put 4 minus x squared over itself in terms of 1. And there's the other half of the addition problem. And now when I add these fractions, I got a common denominator of 4 minus x squared. I can add the numerators, but if you notice, the x squareds cancel, leaving me a 4. And that thing gets parked under a square root. The square root of 1 plus the square of the derivative is going to be the square root of all this. And I know what some of you would do, because I've seen this on your homework. You'll square the 4 on top, you'll square the 4 on bottom, and you'll cancel the square on the x. To that I say yes, no, no. You've got to know your rules for simplifying square roots. You can distribute square roots across multiplication and across division. A fraction is a division problem, so I give the square root to both sides of it. However, you cannot distribute a square root across an addition problem or a subtraction problem. So if you're doing that, stop it. I can't square root both halves of the subtraction problem. I'm stuck there, but I can square root the 4 on top and make it a 2. All right, so this is not looking very desirable because I'm about to park this thing inside of the square root and stick a function in front of it and then try to integrate it. But let's move this up here just so it's out of the way. The square root of 1 plus the square of the derivative ends up being 2 over the square root of 4 minus x squared. All right, so a lot of algebra happened there. Very little calculus. The calculus happened over here. But we just figured out one piece to import into our integral. So let's import it. And while we're importing things into our integral, let's go ahead and import what f of x is equal to, which is the square root of 4 minus x squared. Times the thing that we just figured out, which is 2 over the square root of 4 minus x squared. And suddenly this problem becomes easy. because the square root of 4 minus x squareds cancel. The rule for canceling in a fraction is simple. If you are a factor of the numerator and a factor of the denominator and you match, you may cancel. Factor meaning part of the multiplication problem. The first square root, you can imagine it's over a 1, so it's in a numerator, and it is part of a multiplication problem. The only factor in the denominator is the square root of 4 minus x squared. I can and will cancel those, leaving 2 pi times 2, which is 4 pi. And so we're integrating 4 pi dx from negative 1 to 1. What's the antiderivative of 4 pi? If you said 2 pi squared, you fell for the oldest trick in the book. Pi is not a variable, it's a constant. The antiderivative of 4 pi is 4 pi x. Just like the antiderivative of 4 is 4x, from negative 1 to 1. So, substituting 1 gives us 4 pi, and then minus, substituting negative 1 gives us negative 4 pi, minus minus is plus, surface area is 8 pi. So in the end, this one wasn't that bad, because when it came down to the integration, it was trivial, assuming you remember this was a constant, not a variable. And honestly, even the setup wasn't that bad. I really think the hardest part was adding 1 to the squared derivative. Even that wasn't that bad. Will they all be this easy?